Welcome everyone to our video on percent composition. This is the first in a series of videos where we are going to be taking the mole concept and applying it to learning something useful about chemistry. Specifically, we're going to start off by learning about ratios in chemical compounds. In this video, we are going to define percent composition, and then we are going to learn two different calculations. The first is to calculate the theoretical percent composition of a compound, and then to calculate the percent composition of a compound from experimental data. Our calculations in percent composition and formula depend upon the law of definite proportions. And simply put, this law says that chemical compounds are always composed of the same thing. Specifically, since atoms are constant in their mass, the chemical compounds, which are composed of the same atoms all the time, are always present in the same proportions by mass. For example, H2O is the formula for water. Water is always 2 hydrogens and 1 oxygen. Since those 2 hydrogen atoms always have the same mass, the proportion of mass that's due to hydrogen within each water molecule is constant, or the percentage of mass which is due to hydrogen within a water molecule is constant. Here is the formula that we use for percent composition. Percent composition is often more precisely referred to as mass percent, or percent composition by mass, or percent by mass. Because when we're looking at this, we're looking at a ratio of masses, the mass of the element compared with the total mass of the compound. So we're doing a simple division, the part divided by the whole, mass of element divided by the mass of the compound, and then we're multiplying it by 100% to express this ratio as a percentage. Let's now look at an example and calculate the percent by mass of water. In this example, we are trying to find the percent composition of water. Let's start off by writing the formula for percent composition. Here's our formula. This is what we're trying to find. But the question doesn't really tell us specifically what we're looking for. When a question asks you to find the percent composition of a compound, what it's asking you to find is the percent of each element that makes up that compound. So water being H2O, this question is asking us what percentage of the mass is hydrogen and what percentage of the mass is oxygen. If we look at the formula, we need masses. But the question doesn't tell us about any masses. This is where the periodic table comes in handy. The periodic table provides us with the molar masses of every single chemical element. And we know that if we know the molar masses of each element, we can find the molar masses of any compound. So if we're trying to find percent composition in theory, so without any experimental data, we are going to use the molar masses. Technically, we're using atomic masses, but as we know, the molar masses and the atomic mass numerical values are the same. So let's assume 1 mole of H2O. If we have 1 mole of H2O, the mass of the compound is equal to the sum of the masses of the elements. We have 2 hydrogens plus 1 oxygen for a total of 18 grams in 1 mole of water. Now we also need to have the mass of the element. Well, in water, there are 2 hydrogen atoms. So in the 18 grams of 1 mole of water, 2 of those grams are due to hydrogen. Let's now calculate the percent of hydrogen. So the percent by mass of hydrogen in water is 11.1%. We'll stick with 1 decimal place with these percent compositions. Now let's find the percent of oxygen. Now here's a shortcut. There are only 2 elements in this compound. Those 2 elements make up 100% of the mass. So if hydrogen makes up 11.1%, then oxygen must make up the rest, 88.9%. So we've now found the percent composition of water. 11.1% by mass is hydrogen, 88.9% by mass is oxygen. Let's now summarize the steps we just did. To calculate the theoretical percent composition of a compound, we use the molar masses, or the atomic masses, if you will, from the periodic table. For the element that we're interested in finding the percent composition of, we first sum the molar masses of that element. For example, there were 2 hydrogen atoms in water, so we added together the molar masses of 2 hydrogen atoms. Then we found the molar mass of the compound. We divided the first by the second, and then multiplied by 100%. If we carry out an experiment carefully, we can get masses of individual elements that make up a compound, and then also have the mass of a compound in total. This will be a useful tool for us in determining the composition of a compound and the formula of a compound. Take a look at this example, and then we're going to go to the whiteboard and solve this problem. I've started off by writing out the given information. Let's next write out the formula. The question gave us all the information we need. So try right now, pause the video, and calculate the percent composition of sulfur and that of zinc in this compound. Here are the percent by masses of sulfur and zinc in this compound. Remember that we will round our percent compositions to 1 decimal place in all examples that we do. The example we just did will be important in lab activities and also for determining the identity of unknown compounds. Specifically, it will help us determine the formula of an unknown compound. One thing to note is that when you use experimental data, your percent compositions will be close, but not always precisely the same as those that you found when you calculated the percent composition from the periodic table. Okay, but this is just due to experimental data and is expected. Where does this experimental data come from? Well, typically it comes from carrying out synthesis and decomposition reactions. Remembering from previous science courses that synthesis is a reaction where two smaller elements or compounds come together to form a single product. And decomposition reaction is where a compound breaks apart into simpler components. The synthesis and decomposition reactions that are most useful is where one of the reactants, at least, of a synthesis reaction, and at least one of the products of a decomposition reaction are elements. A question I'll leave you with is, can you think of why these two types of reactions are specifically useful, and maybe why they're more useful than other types of reactions such as double displacement or single displacement reactions?